Welcome to the Deep Dive, the part of the All Sorts podcast where we really get into the weeds on fascinating subjects. Today we're embarking on a pretty cool adventure, actually.
Yeah.
Into the world around us, the solid stuff, but seen through a kind of invisible cosmic rain. We've got a stack of sources here, all pointing towards this incredible technique called muography.
That's right, or muon tomography, you'll sometimes hear it called.
Right, tomography. And it basically gives us this amazing ability, almost like X-ray vision, but, well, much more powerful.
Exactly. It lets us see inside things using these naturally occurring particles, muons.
Muons.
Imagine this constant stream, almost like tiny messengers from way out in space. They get created when cosmic rays hit our atmosphere. And the key thing is their penetrating power. It's just, well, extraordinary, much, much better than standard X-rays.
So you can see through really thick stuff.
Precisely. And by tracking how these muons go through something or how they scatter off it, we can build up a picture of what's hidden inside, the density, the structure, sometimes even what it's made of.
Wow, okay. And the sources we have suggest this is being used in, well, all sorts of surprising ways.
Oh, absolutely. Across so many different fields. Get ready for some moments, I think. Seeing the unseen, essentially.
I love that, seeing the unseen. And hey, if you're enjoying this journey into hidden worlds with us, make sure you dive into everything else we offer on the All Sorts Podcast YouTube channel. Seriously, explore our universe of deep dives. Like, share, subscribe. It really helps us keep bringing you these explorations.
And for those quick hits of curiosity, find the All Sorts Podcast on X, Instagram, and Threads. We're everywhere.
So our mission today. Let's unpack how muography is unveiling secrets. Expert, maybe start with the basics. These muons. What exactly are they?
Right. So as you said, muography, muon tomography, same thing basically. These particles, muons, they start their life way up, high in the atmosphere, cosmic rays, mostly protons, zip in from space, smash into air molecules. That collision creates a whole shower of other particles, things like pions, kaons. And those particles decay very, very quickly into muons and neutrinos.
Okay, so they're born from cosmic collision.
Exactly. Now, muons themselves, they aren't stable. They have a really short lifespan, technically.
But they reach the ground.
They do, because they're traveling incredibly fast near the speed of light. And thanks to Einstein's relativity, their internal clock slows down relative to us. Time dilation.
Ah, relativity in action.
Yep. So it stretches their lifespan enough for a good number of them to make it all the way down to the Earth's surface. In fact, right now, about 1 muon is passing through every square centimeter of you every minute.
Wow. Okay, a constant natural shower.
A constant, natural, invisible shower of these particles.
And you mentioned their penetration power is key, better than X-rays. Why is that difference so significant?
Well, it comes down to how they interact with matter. Muons are, relatively speaking, less interactive than X-rays or gamma rays. Think of trying to get through a really dense hedge. X-rays are like tiny pellets. They might get stopped easily by the outer leaves and twigs. Muons, though, especially the higher energy ones, are more like, tiny bullets that can punch deeper through the thicker branches inside.
Okay, that makes sense. They just don't get stopped as easily.
Exactly. So they can travel through meters, even kilometers of rock or concrete or water, stuff that would completely block X-rays.
Yeah.
This opens up imaging possibilities for things we just couldn't see into before.
Right. So we've got this constant rain of penetrating particles. How do we actually use them to, make an image?
Good question. There are two main ways based on our sources. The first one is often just called muography, but more specifically, it's muon transmission radiography.
Transmission, like sending something through.
Precisely. It's quite similar, conceptually, to how a medical X-ray works. You basically count how many muons make it through the object you're looking at. If there's a denser region inside, it will absorb or maybe deflect more muons.
So fewer get through on the other side.
Fewer get through. So you end up with a lower muon count, or flux, behind that denser area. By mapping this flux across the area behind the object, you get a 2D picture, a sort of density shadow puppet show. We call it a muogram.
A muogram. Okay. Lower density means more muons get through. Looks brighter.
Usually, yes. Brighter means less dense. And if you take measurements from different angles around the object.
Oh, like a CT scan.
Exactly like a CT scan, computationally.
Yeah.
You can reconstruct a full 3D density map of the inside. Tomography.
Okay, so transmission gives us density maps, 2D or 3D. What's the second technique?
The second one is called muon scattering tomography, or MST.
Scattering, so how they bounce off things.
Sort of, yeah. Instead of just counting how many get through, MST looks at how much the muons get deflected or scattered from their original path as they pass through the material. They interact with the atomic nuclei inside. and the angle they scatter at. Well, that angle is related to the atomic number, the Z number of the atoms they hit.
Atomic number, so like lead versus water.
Exactly.
Yeah.
Heavier elements, higher atomic number materials like lead or uranium, tend to scatter muons more strongly at larger angles than lighter materials like water or carbon. So by carefully tracking the incoming path and the outgoing path of lots of individual muons and measuring those scattering angles.
You can figure out what kind of material is inside, not just how dense it is.
Potentially, yes. It's particularly good for spotting small amounts of high Z material hidden inside lower Z stuff, like, say, finding shielded nuclear material inside a cargo container.
That's incredibly powerful. So not just density, but composition, too.
It gives you information related to composition, yeah. It's a different kind of insight.
Okay, this is fascinating stuff. Now, our sources, they cover a huge range of applications. Let's start with industry. How's muography being used there?
Right, the industrial sector. It's popping up as a really useful NDT technique.
NDT, non-destructive testing.
Exactly. Ways to check things without breaking them. Think preventive maintenance, quality control on production lines. A big plus here is that it's non-contact. Muons go through air easily, so the detectors don't need to touch the machinery.
So you could inspect, say, a hot pipe or something running.
Potentially, yes. It makes it great for large, complex systems, maybe even while they're operating. And often in industry, you're not trying to map a totally unknown object. You have blueprints.
Yeah, you know what it should look like.
Precisely. So you're often just looking for deviations, small changes like a blockage, or maybe the wall of a tank getting thinner than it should be. That simplifies the image analysis a bit because you're hunting for anomalies against a known background.
Makes sense. Spotting the difference. Okay, what about big structures? Buildings, bridges, structural engineering. Sounds like a prime candidate.
Oh, definitely. Especially for things made of dense materials, like reinforced concrete. That's where muon absorption radiography, the transmission method, really shines.
Because other methods struggle with concrete.
They can, yeah. Traditional NDE like ultrasound or infrared or GPR ground-penetrating radar, they have limits, especially with thick concrete or lots of steel rebar inside.
Right, the rebar would mess things up.
It can interfere, yes. Muography kind of bypasses that. So the advantages are pretty clear. It's non-destructive, obviously crucial for historical buildings or critical infrastructure like dams and bridges. It can find hidden problems, voids, cracks deep inside, and potentially even detect corrosion on the steel reinforcing bars.
Corrosion? How?
Well, rust is iron oxide. It has a slightly different density and composition than solid steel. Early research using muon scattering data and machine learning suggests it might be possible to pick up those subtle changes.
That would be huge for bridge safety.
Absolutely. And imagine continuous monitoring. You could set up detectors and track the health of a structure over years, see how density changes, maybe detect problems developing slowly. Plus, it's good for underground things, too. Tunnels, hidden cavities.
And it uses natural cosmic rays, so no need for a big artificial radiation source?
Correct. Which can make it more cost-effective in some scenarios. Certainly simpler logistically than bringing in, say, a large X-ray machine for a bridge. It's often seen as complementary to other techniques.
So we're already seeing it used on tunnels, dams, historical sites?
Yes, the sources mention examples of all of those. Researchers are using different muon methods, 2D density maps, full 3D tomography, differential methods to spot subtle changes in density over time, scattering analysis for composition hints, even tracking tiny movements within a structure. And as I mentioned, there was that first experimental proof showing you could actually get a tomographic 3D image of the inside of a concrete block using muons. It's moving from theory to practice.
Incredible. Pinpointing rust inside concrete without touching it. Amazing. Okay, let's shift gears completely. Geology, the Earth itself, geosciences, geomorphology. How does muography fit in there?
It's seen as a really novel tool here, especially for looking at density variations in geological materials. Its real power, potentially, is for long-term monitoring. Think about processes that change density underground over time.
Like water moving around.
Exactly. Groundwater movement, how soil freezes and thaws, ground frost, glacier dynamics, the opening or closing of fractures in rock, even magma moving up inside a volcano before an eruption.
Volcanoes, right. Density changes would be key there.
Absolutely. Because the muon source, the cosmic rays, is constant and free, you can potentially install detectors and just leave them running for months or years. That gives you a way to track these slow, dynamic geological processes that are really hard to monitor otherwise.
A natural, always-on density scanner for the planet? What specific things are being done?
Well, people have used it to find hidden geological faults, map groundwater levels, identify barriers in the ground that stop water flow, look for density differences in rock formations, also mapping natural caves, and yes, monitoring volcanoes is a big one, looking for those density drops that might signal magma rising.
And future possibilities.
Oh, lots. The sources suggest looking at soil erosion, how fractures develop underground, how hill slopes change over long periods, understanding groundwater reservoirs better, river channel erosion, getting inside glaciers, landslide mechanics,
Wow.
even looking at impacts of climate change on some of these systems through density changes. It's a wide open field.
From bridges to volcanoes, the scope is just mind-boggling. And then archaeology. This sounds like something out of Indiana Jones.
Yeah, well, maybe not quite with a whip, but yeah. Actually, one of the very first uses was archaeological. Back in the 60s, the physicist Luis Alvarez, a Nobel laureate, used muon detectors to look for hidden chambers in the pyramid of Chephren at Giza.
Did he find anything?
Didn't find a hidden chamber in that case, but it was incredibly pioneering. It showed the concept could work. More recently, you had the Scan Pyramids project. That did use muography, among other techniques, and famously found that large void, the Scan Pyramid's big void, inside the Great Pyramid.
I remember hearing about that. And another structure, too.
Yes, a sort of corridor-like structure near the entrance as well. Muons were key to those discoveries. It's also been used at the Pyramid of the Sun in Mexico, found a low-density zone there.
Right.
And a really nice example from Italy, around Echia. They used muography to create 3D images of known caves and discovered previously unknown cavities inside the mountain.
So it works for finding new stuff and checking the condition of known structures.
Exactly. Assessing structural integrity of ancient sites without drilling holes is a huge benefit. There are even studies looking at whether it's feasible to image the underground tomb of China's first emperor using muons.
A non-invasive peek into history? That's incredible. Okay, switching again, modern concerns, nuclear security, non-proliferation efforts. How can muons help there?
This is a really critical application. Muon tomography, especially the scattering method, MST, is very promising for detecting shielded nuclear materials.
Because the muons get through the shielding.
Precisely. Things like uranium or plutonium are very dense high-Z materials. They're often shielded with lead or other heavy materials, specifically to block typical radiation detectors, like gamma rays. But muons can punch through that shielding. And MST can pick up the distinctive way muons scatter off those high-Z nuclei inside.
So you could potentially scan a whole truck or shipping container.
Yes. It allows you to spot suspicious, dense objects hidden inside otherwise normal cargo. This is also being looked at for treaty verification, like the new START treaty between the U.S. and Russia.
How so?
Because its passive use as natural muons and highly penetrating, you could potentially verify aspects of nuclear warheads without needing to, say, open them up and reveal sensitive design secrets. It sees inside without being too intrusive.
That's a clever balance. Are there systems actually deployed?
There are. The sources mention the MMPDS port scanner in the Bahamas. That uses MST to scan cargo containers for nuclear materials, but also explosives and other contraband. It's a real-world example.
A powerful tool for security. What about inside the nuclear industry? Reactors? Waste?
Also very relevant there. After the Fukushima disaster, for instance, muography was one of the techniques used to look inside the damaged reactor cores.
To see what had happened.
To confirm the extent of the meltdown, basically. In such a highly radioactive environment, you can't just send people or cameras in easily. Muons offer a way to get an image remotely.
Non-invasively.
Critically, non-invasively. It's also being developed for checking spent nuclear fuel inside the big, sealed, dry storage casks.
To make sure the fuel is still there? Accountancy.
Exactly. For nuclear materials accountancy and safeguards, it helps verify the contents without having to open the cask, which is a complex and hazardous operation.
Yeah.
They even imaged a reactor mock-up at Los Alamos using a portable system called the Muon Mini Tracker, the MMT.
Providing vital information where access is dangerous or impossible. Okay, this next one sounds wild. Planetary science. Using muography off Earth.
It sounds like sci-fi, but yes, it's being seriously considered. Cosmic rays exist throughout space, not just near Earth. So if a planet or moon has even a thin atmosphere, or if cosmic rays hit the surface directly, they can generate muons there too.
Mars.
Mars is a key target, yes. Calculations suggest Mars's atmosphere, though thin, should produce enough muons for muography to be practical on the surface. Imagine a future Mars rover drilling down, but also using muography to map out density variations deeper underground.
Looking for water ice, maybe? Or different rock layers?
Exactly. Subsurface geology, resource prospecting.
Yeah.
NASA has actually assessed using it for asteroids and comets, too, imaging their internal density structure.
Wow. Using cosmic rays to do geology on other worlds. That's amazing. Any other niche applications mentioned?
A couple of quick ones. There's this emerging field called hydrospheric muography.
Hydro, undersea.
Yep. Early tests in Tokyo Bay showed it might be possible to study geology beneath the seabed using detectors placed underwater. Maybe even look for marine resources.
And the other one?
Carbon capture and storage, CCS. The idea is to inject CO2 deep underground. Muography has been proposed as a way to monitor those storage sites long-term to make sure the CO2 is staying put and not leaking out by tracking density changes.
Checking the integrity of the storage makes sense. It really does seem the applications keep expanding.
Yeah.
So technically, what's happening to make all this possible? What are the innovations?
Well, the field's definitely not standing still. Detector technology is constantly improving. Things like micromegas detectors are offering better spatial resolution, sharper pictures, plus ongoing improvements to more established detectors, scintillators, the photographic emulsions, gas detectors.
And the analysis, getting the image from the raw data.
Huge area development, creating better algorithms for reconstructing the images, cleaning up the noise, and increasingly using AI and machine learning to find subtle patterns in the data, perhaps like we mentioned with detecting rust, or maybe to speed up the image reconstruction process, or fuse muon data with other sensor data. We're also seeing next-gen systems. There's a Canadian detector called CREEP-TT mentioned, which tries to measure both the scattering and the momentum, the energy, of the muon.
Why momentum?
Knowing the muon's momentum helps refine the scattering calculations, potentially leading to much better resolution, especially for MST. So people are developing portable muon spectrometers to measure that momentum out in the field. And there's MuCat muon computational axial tomography, basically refining the techniques to get those really good 3D images from multiple 2D views, just like medical CAT scans.
So better detectors, smarter software, more sophisticated techniques. The toolkit is getting much more powerful.
Definitely. It's pushing the boundaries of what's possible.
But realistically, there must be limits, right? It's not magic X-ray specs.
No, absolutely not. There are definite limitations to keep in mind. Generally, the image resolution from muography isn't as sharp as you might get from, say, a medical MRI or CT scan, or even high-frequency ultrasound in some cases. It's often about seeing larger features or bulk density changes.
Okay, so maybe not seeing tiny details.
Not usually, no. And interpreting the data isn't always straightforward. You often need quite complex analysis and modeling to understand what the muon signal actually means in terms of the material inside. Background noise is also a factor, stray radiation, variations in the cosmic ray flux itself due to atmospheric conditions. You need good calibration and data processing to handle that.
Right, the atmosphere isn't perfectly constant.
Exactly. And then there's something called the volume effect. This can be tricky. Imagine you measure a certain drop in muon flux. Is that caused by a really large area of slightly dense material or a very thin layer of extremely dense material?
They could block the same number of muons overall.
They could. So differentiating between those scenarios can be hard, just from the muon data alone. Having good information about the object's external shape beforehand really helps resolve that ambiguity.
So you need other information sometimes.
Often, yes, at a practical limitation, especially for transmission muography. Sometimes you need detectors underneath the thing you're looking at. That's not always possible if you're looking at a mountain, for example, or deep underground structures from the surface.
Right, you can't always dig a tunnel underneath. Okay, so powerful, but with caveats.
Like any technique.
Yeah.
But its unique strengths, that incredible penetration being non-invasive, using a natural source, make it invaluable for specific problems where other methods just can't work.
Absolutely. Well, this has been just fascinating, a real deep dive into muography, from pyramids and volcanoes to nuclear security and maybe even Mars geology. It's clear this is a remarkably versatile tool.
It really is.
Using nature's own particle showers to reveal secrets hidden inside solid matter. It's quite poetic, actually. It really makes you wonder, doesn't it? What else is out there, hidden from view, that muography might let us see next? What structures, what processes, what history is waiting to be uncovered by these invisible messengers?
That's the exciting part. We're still exploring the potential. It's a great example of taking fundamental physics and applying it in really creative and useful ways.
Couldn't agree more. Thank you for joining us on this exploration into the truly captivating world of muography. We really hope you found it as eye-opening as we did. Please do continue your own journey. Look up some of the projects we mentioned, explore the applications that sparked your curiosity. The information is out there. And now, dear listener, as those cosmic muons continue their silent, ceaseless path through everything around us, may your own search for understanding be just as persistent, just as revealing. Remember to like, share, and subscribe to the All Sorts podcast on YouTube. There's a whole cosmos of deep dives waiting for you there. And catch us on X, Instagram, and Threads. Follow the All Sorts podcast for all the latest insights and intriguing explorations. Until our next journey into the depths of knowledge, keep looking deeper, keep questioning, and keep exploring the amazing universe we inhabit.